Hello, in this video we are talking about taking measurements from stars. What can we actually figure out? A surprising amount given the little bit of information we have. So we're going to look at the types of measurements you can take, one in particular called parallax, and recap a little bit of how you can do some math, some astrophysics, some genuine astrophysics on star stuff. Okay, just to give you an idea, this is a Hubble telescope picture of Proxima Centauri, which is the closest star to us besides the sun. All right, this is like our nearest neighbor, and that's as good as we got. The best close-up picture of a star we can get looks like this, and that is like a smorgasbord of data right there. The number of pixels you got, oh my gosh, so many pixels of information. Many stars. You don't get more than a few pixels. They're so far away. But that's like the best we got. So studying this thing, it still comes down to you just got kind of a blotch of light, and you got to be clever about what you can figure out about how light stuff works. All right, so we're working with teeny bits of light here to figure all of this out. It's pretty amazing. Here's one thing that we have figured you can do is you can use the idea of parallax to measure how far a star away if it's close. So this works for nearby stars. Here's the idea with parallax. Parallax, we've talked about in terms of like measuring stuff. You know, you got to make sure your eye level. If you're reading, lines on a beaker or something. If you're looking like offset from an angle, it'll change where something appears in your field of view. So the idea is the Earth is moving all the time. It's moving in a circle around the sun. And so this sort of back and forth motion means if you fix your eye on a star that's not too far away, as you move from like, what we could call in this picture here, the left side of the orbit to the right side of the orbit, you kind of see the star from different angles, like against the background. All right, here's the way you can try this if you want to try a little experiment. Stick your thumb out in front of you and stare at it. Yes. Okay. And then move your head side to side and like look at your thumb in terms of the wall or whatever background is like further behind your thumb. You will see your thumb looks like it goes like left and right. Like stick your thumb on top of somebody's head and then move your head left and right. You'll see your thumb move like to the left side of their head, to the right side of their head, right? Because your thumb is closer than their head is. And your field of vision kind of goes through like that. So that's what we do. We do that with a nearby star. And there's stars that are far enough away that we treat them like they're just fixed in place because they don't really have any parallax at all. They're so far. And so what we do is we measure an angle here, a parallax angle. Do draw this picture. They like to ask you how this works and even have you draw this picture. They've had you do once or twice. So June and December are not like special. You just need 2 points that are, half a year apart, 6 months apart. So you're on opposite sides of the orbit to get the maximum angle measurement you can get. So you measure like where that star appears against this kind of background at one point in time. 6 months later, you measure it again. You will see it has moved, and you measure the angle it's moved by. And you do some right triangle stuff. You do some SOHCAHTOA. We know how far away we are from the sun. If I know this angle, I can find the distance. It's just right triangle math. That's it. That's astrophysics. Yeah, so that's what we do. That's how you measure parallax. Okay, here's some pictures to give you an idea of what this kind of looks like with some real data. So there, as you can tell, I bet you can tell just by looking which stars are the closest and which stars are the furthest. What do you think? I'm thinking the stars that move back and forth the most are the closest. Yeah. Okay, but that's kind of what this looks like. So you can measure on a telescope, how far these things have gone side to side over the course of 6 months or so and math it out. These angles are super small. Here's a little fun reference to give you an idea of like how big angles in the night sky are, because your whole field of vision is like 180 degrees. Been all the way around, that's 360 degrees. So like your pinky at arm's length takes up about 1 degree of like, space on the sky. Well, all of these parallax angles are way less than even 1 degree. And so we have special units for really small angles. which we break up like a clock into minutes and seconds. We call them arc minutes and arc seconds. So a degree we can break into 60 arc minutes, and an arc minute you can break into 60 arc seconds. So there's something like 3,600 arc seconds in a degree. Here's another way to think about 1 arc second. If you take a penny and put it 4 kilometers away from you, okay, that will take up 1 arc second of, your field of view. You can't see it. It's teeny tiny. It's so small, an arc second. But that's the units we're dealing with a lot here and the precision we can measure this stuff in. Okay, so this brings us to, we're going to get to a version of the parallax equation. That's like a pretty easy way to use it. One thing baked into that equation we're going to do is a different unit called a parsec. And a parsec, despite, hate to say it, despite Han Solo's phrasing, a parsec is a unit of distance. So it's measurement of distance, and it's like a very specific one. It is the distance where a star would have a parallax angle of 1 arc second. This distance, and if you find a star where it's like just the right distance away, that you measure its parallax angle and get 1 arc second, we call that distance the parsec. Okay, that's a weird one, but that's what it means. The parsec, the sec is for second, an arc second, and the par is for parallax. So parsec is like parallax of 1 second. There's some information about the parsec and other spacey astro distances in here that you want to know. Okay, so first you get a light year. And a light year, that's how far light goes in 1 year. Go ahead, multiply the speed of light by the number of seconds in 1 year, and you get this number. That's what we call a light year. A parsec, this is the definition you want to know. And they give us a parsec to light years conversion. So in other words, to get to this star, that's an arc second of parallax measurement from Earth. It would take light 3¼ years to get to that star. Okay, and there's one other thing in there that is occasionally used, especially sometimes with Kepler's law and stuff, is the astronomical unit, the AU, and that is the distance between the Earth and the Sun, which is there, 1.5 times 10 to the 11 meters. All right, so that's the Earth-Sun distance. So that's like one leg of the triangle we would use here to find this distance. All right, but those are in your data booklet, so when you see stuff like light years, parsecs, AU, head over there and convert. Okay, other parallax trivia. It's pretty good for close stuff, but the further away something is, the parallax is too small to measure after about 100 parsecs or 300 or so light years, which space-wise is like very, very, very not far. But there's a ton of stars within that distance. The trouble here is the angles are really small, and especially when you take the Earth's atmosphere into account, which messes with your light and bends it in such a bit. So it gets too hard to read through the atmosphere. You can take measurements from space, and we do have some space-based telescopes that we do parallax measurements with. And those you can get a lot further because the light doesn't have to go through the atmosphere, like 1,000 parsecs, 3,000 light years or so. All right, is the range. So it works for close stuff. All right, let's look at where the equation comes from. It's SOHCAHTOA. If I have this parallax angle, we're going to call it P. It would be kind of opposite over adjacent, so we could do a right triangle thing where we'll call this X. We can do a small angle approximation because we're talking angles way less than 1 degree. So it is definitely fair to say the tangent of the angle is basically equal to the angle of itself. We're talking radians now for the moment. And so the distance to the star, you would just do the lazy version of tangenting. Take the distance, the length of the opposite leg divided by the angle. There you go. That's your distance. Okay. The equation is fantastic because it's one of these lazy, weird unit physics equations. We have baked into the equation these distances, an AU and an arc second. So we've made it so that the equation will just give you a distance in parsecs without having to do any conversions, any trig, anything like that, if you put in the parallax angle in arc seconds. Because this idea, one idea of doing this equation is, okay, if the distance is 1 parsec, we're saying that's the distance where you get 1 arc second of parallax. And we're going to just call this 1 AU, because that's like this length. It's 1 distance away from Earth. And because this all works, and this is how we define the arc second, or the parsec rather, we're able to just truly put in parsecs here, put in arc seconds here, you get one from the other. That's all you have to do. All right, so this equation is set up so that you can just put in the angle in arc seconds. 1 divided by that number is the distance away that the star is in parsecs. So it's one of these weird data booklet equations where they like put the units in here in parentheses, which is super weird. But this is just distance equals 1 over p, d equals 1 over p. The d is a thing that works in parsecs in this equation. The p is a thing that works in arc seconds. Okay, so that's parallax. That's kind of the new method of doing stuff, which again is great, and you can get some really good data for nearby stars. But some stars are way further away, and you can't do parallax. You can do a lot of math you've already learned how to do. Because we learned a lot about this stuff when we learned about light and how light transfers energy, especially. So we're going to use those equations. Here's one idea you got to keep in mind if you look up at the night sky and you see 2 stars and one's bright and one's dim. Which one is closer? Which one is bigger? Hard to say. Because, okay, in this case, like A maybe looks brighter than B. That doesn't mean A is giving off more light than B, though, because it could be closer to you, right? And one could be far away. So we can measure how bright the light is, but we don't know if something's bright because it's close or if it's bright because it's powerful. Well, with some other equations, we can kind of figure it out. But we can measure brightness is the thing we can kind of really measure here from Earth. So a lot of times we're going to be dealing with, we measure B. B is just you stick out a little solar panel that measures more or less and see what you get, watts per square meter. Remember, that's an intensity. And we can figure out all kinds of other stuff with these equations based on the temperature of the star, the size of the star, the luminosity, the brightness you would measure, how far away it is, the temperature, the peak wavelength, all of those things are kind of connected together. So more or less, if you're doing like star math and you're not doing a parallax thing, you're going to use some combination of these equations to figure out what you got to figure out. All right, most important stuff to remember with all of these, though, is that L, luminosity, is power. It's watts, it's joules per second. It's the rate of energy coming off of the star. And doesn't depend on where you are. That's not a relative measurement thing. That's just how much energy the star is making. Right? And then B is the intensity. That's based on how far away you are. Kind of what fraction of that energy do you catch every square meter? How bright does the star look to you in a watts per square meter way? That's intensity. Okay, we know all these other equations, but little d is the distance, in this case, the star is away. A is the surface area of the star. T is the temperature of the star. That's the peak wavelength given off by it. Okay, so those are the equations to use. Go ahead and try them. Here's a fun type of problem you might see. Sirius, the dog star, a very bright blue star in the sky. You measure it, it's pretty darn bright. That's how bright it is. That's the brightness in watts per square meter. We know the radius from some other stuff, so that'll let us do what we got to do. If we can also look at the peak wavelength and measure that the surface temperature is close to 10,000 Kelvin. You give this a shot. Can you cobble together those equations from the previous slide, equations from B.2, and figure out how far away is Sirius from Earth given this information? And just to practice a conversion, turn it into light years. Try it out and see how you do. I'll have a solution posted. The answer you should get is 8.62 light years. So see if you can get yourself to 8.62 light years. All right. And if you did, congratulations. You did some astrophysics. Great job.